Good evening, Math 30-1. Welcome to part one of the journey in log and exponential functions. And it really is going to be tying together all the things that you've learned along the way. It shouldn't feel like there's a lot new. So for example, we need to remind ourselves about form, dressing up the pig with lipstick, right? So if I was to change this to logarithmic form, what would it look like? Well, it would make sense to say 2 to the minus 3 is equal to 1/8. And now I can take the log of both sides and I would take it to a base of 2. And this statement would be equivalent to the log of 1/8. The log of 1/8 base 2, is equal to minus 3. Same statement stated as a log. Remember, base, number, exponent. Not any different than what you see here, base, number, exponent, right? Just worded differently. So how would I express this in logarithmic form? Well, 5 to the 0 equal to 1 would be the same thing as saying, well, what if I took the log of 1 to a base of 5? That would give me 0. Again, base, number, and exponent. Okay? All right. When we continue on, what about writing a log? What about the log of 1 over 16? We can manipulate these things in exponential form. That's the same thing as saying 2 to the minus 4 equals 1 over 16. Right? We've done this before. This is a review. So what about this statement? Well, it's a little bit trickier because you probably need to deal with this 3. You need to work with it, right? So you might, well, how does that work out? Exponential form, that doesn't even seem right. But remember that you can't forget that what we need to do in terms of laws of logs is I need to put this 3 on top of that 5. So this statement could be written as the log of 5 to the exponent 3 base 5 is equal to 3. Therefore, right, when you rewrite it as an exponential form, you get to this statement. But you have to use the laws of logs to put that 3 back on top of that 5, right? So we're just reviewing lessons 6 and 7 that leads up to this, right? So now, what if I'm solving a log equation? One of the rules is use exponents. Rewrite it as an equation by using exponential form. So that's one of the strategies. Strategy 1, if I see it, do this. So I've got this log equation. Oh my, how am I going to solve that? Well, first strategy, put it as an exponential form. Rewrite the problem. If you rewrite it as 6 squared equals x, well, that's pretty an easy question, right? That just means that x equals 36. All right, what if I had to solve this question? The log of 1 over 25 base 5 is y. Now, some of you guys might know automatically, oh, I know what the answer is because you see these things intuitively. If you don't, again, we've talked about this, rewrite it as a exponent, right? 5 to the y is equal to 1 over 25. Now we can use same base strategy. 1 over 25 equals 5 squared. So that means 5 to the y equals 5 to the minus 2. So y equals minus 2. Okay? So rewriting things as an exponent is a really good, valid strategy. Okay? Strategy number 2. What if we equate the two logs? These are both algebra. The property of equality. We used this, just reviewing, we used this when we did exponential equations using same base, right? So same rule applies for logs because logs are exponents. Remember when we solved 2 to the x equals 4 to the x plus 3? If you put things in the same base, 2 to the x, just reviewing, 2 to the x is equal to the 2x plus 6. So that means that, therefore, x would equal 2x plus 6. So that means that x would equal 6. Oops. No, silly. That would mean that if I took the x to this side, x would equal, I bring that over there, x equals minus 6. Okay? All right, so now, how does that look like with log? Same base strategy? Well, If we have the same base, then what's under them must be equal, right? So the number that you took the log of, if the two logs are equal, then those two numbers must be the same. Same as we did with the exponents up here, you guys, okay? So for the equations with log, if we express both sides, then and the bases match, then those two arguments must be equal. So for example, I've got this situation. The only way this can possibly happen is if 2x minus 1 is equal to 11. I've got them as single logs with the same base, therefore x must equal 6, okay? Using the same base strategy. The only thing you need to be aware of is you should be thinking about restrictions, and we talked about this in Math 20. 2x plus 1 has to be more than 0. You cannot have the log of 0 or a negative, right? It got to be greater than 0. So for 2x to be greater, 2x minus 1 to be greater than 0, x has got to be greater than a half, okay? Just solving that equation. Next up is this equation. Notice I'm already working on restrictions. We'll ignore that for now. But if you're using the graphical method, you say, well, I don't really know this algebra stuff. I could graph these two equations, log 4x plus 10 base 3 and log x plus 1 base 3. And we talked about using our calculators. If we graph those as two separate arguments, oopsie, now we already know what the answer is using algebra, but let's pretend we weren't that smart, right? Since the bases are both 3, we set the arguments equal, and we get x equals minus 3. Now, we think that our algebra has set us free, but when we graph these two and we use a graphical method, we notice that, wait a second, these two graphs never intersect. So how could we be getting an answer of x equals minus 3 if there is no answer according to the graph? And that's a reminder of why we need to check the restrictions. X must be greater than or equal to negative 5 halves. Now you might see on the side the little stop man. The one function has a restriction of, the one restriction has x is greater than minus 1, but you need to pick the restriction that satisfies both. And so like we talked about in Math 20 in radical functions, this is the overriding restriction. If your answer doesn't fit within that restriction, then it's extraneous, and that's what happened in this case. The algebra said that negative 3 is the answer, but the restriction says you can't. And there's another way you could have done it. If you plug in minus 3 into the question up here, you end up with the log, just a quick little check, and you end up with the log base 3 of minus 2, and that can't happen. That's another reason it's extraneous. You don't need to see the graph to see it's extraneous. That value creates a log of a negative, and that can't happen, right? So we can't have it. We have to be aware of restrictions as we do these questions, okay? So in this question, there is no solution. You can't have it, okay? Okay, so let's start dealing with some real equations, and you can start flying on your own. And you can ignore this, use the laws of logs and the equation property. We're not using graphical anymore. Solve these algebraically, right? So how do I use my laws of logs? Well, the first step is I could isolate the x and get the numerical parts over. And when I do that, right, when I do that, I end up with the log of 72 divided by 12. And now I can equate these two because I've got single logs and the arguments have to be equal. So 72 over 12 equals x, and that means that x equals 6. Does this fit within the restriction? What's the restriction? The restriction was x had to be greater than 0. And you can simply check by putting 6 in there. Does that cause a problem? The log of 6, not a problem, right? We can look at it graphically if we want. I'm not going to do that. You can play with that if you want. When you go to solving this question, once again, we think of a restriction. Is there a restriction? Well, x squared minus 14 has got to be greater than 0. That means my answers, my x squared has got to be greater than or equal to, greater than 14. Now, the other restriction was 5x. 5x has got to be more than 0. That means that x is greater than 0. The overriding restriction is root 14, right? So now my arguments are equal. I solve it. It's a quadratic. I take it to one side, I factor it, and I get two answers of x equals 7 and x equals -2. Hold it. I got to be greater than root 14. If I plug in one of these answers, like -2, if I plug that in, that doesn't work. And that means that -2 is extraneous. Okay, you can't have that one. Does not work. Okay. So nothing fancy. We're using this get equal logs together and then go from there. How about this one? Ooh, a bigger question. Again, using the laws of logs, where do we go from here? So I've got two logs here. I'll use the laws of logs. I can put those two things together. That's division. And if I put these two arguments together, because now log 7 equals log 7, I get 2x plus 2 over that equals x plus 1. Nice. I cross multiply, and I end up with another quadratic. I factor, I find answers of x equals -3 and x plus 1. Now we can go look at restrictions, but the other way, the other way is that we can just plug these in. And if you plug in 3 to the beginning of the equation and think, do I get 0 or a negative? And if you don't, you're good. So I'm not going to go through all this work that I've crossed out here. I'm not going to do it. Just sub and look is what I'm saying here. So when I plug in 3, and if this doesn't make sense, ask me tomorrow. When I plug in 3 here, I get 6. That's not a problem. Plug in 3 here and I get 2. Plug in 3 here and I get 4. Question number, or in other words, x equals 3 is fine. If you plug in -1, and I'm just going to circle that in blue, when I plug in -1 here, plugging -1 here, and I get 0. Stuck. That's done. As soon as you get the log of 0 or a negative, it's done, and that is why that one is extraneous. You could look at the restrictions, and the restrictions have to be x is greater than 1, but you could also just sub and look. I would never do all this work. Never, 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 never. But you do need to be aware that when you plug in, you can't get the log of 0 or negative. Okay, that's undefined. All right. Therefore, the only answer is x equals 3. And sometimes you get situations like this where you don't have a log on both sides. So there's going to be two different strategies. One of them is to just put these two together as a log. There is a typo right here, and I'll fix that. So now you say, okay, well, these two can go together, and I get the log of x plus 1 times x minus 5, which then creates, oh, I can now take and change it to exponential form. 7 to the 1 is equal to, x plus 1 times x minus 5. And then you would carry on like that, and you would solve this quadratic equation and go from there. That's one way. The other way is to change both sides to logs, right? So if I changed this 1 to a log situation, you could say, well, that's really equal to the log of 7, base 7. And now you end up with basically the same situation. Doesn't matter which way you do it, as long as you realize when you have a coefficient, then you need to do something, and maybe it's changing it to exponential, and maybe it's turning that coefficient into a log. Either way, you're going to get answers of x equals 6 and x equals -2. And our restriction was x has got to be greater than 5, so obviously -2 is extraneous. And if you plug it in, you can see I get log of -7. That won't work. All right? And you are now at part 2. So please do the part 2 notes, and we will see you tomorrow.